July lectures in physics, even though, of course, we're now into August. I'm Alan Spargo. I'm the acting head of the School of Physics here, and my job tonight is to introduce our speaker, who is Dr. Jeff McCallum. Jeff is a Queen Elizabeth II Fellow in the School of Physics here, and has had a very distinguished research record, and has established in this school a very, very fine research group working on various important problems on the doping of silicon. And of course, many of you will realise that this problem and the others associated with it represent the essential step towards the fabrication and production of not only silicon but other and microelectronic devices based upon silicon technology and all the devices that follow from it. And tonight he is going to address us on the topic of the 50th anniversary of the invention of the transistor. And this is very topical, of course, because this year represents the 50th year after the invention of the transistor, and I'm sure that everybody in this room has, one way or another, held many dozens of transistors in their hands, whether or not they knew it or not. And Jeff is going to talk to us a little bit about the inner workings of these fascinating and very important devices that have indeed revolutionised our modern society and represent perhaps the most fabulous experience of transfer of fundamental physics operating in the research lab into industry and technology. Jeff McCallum will now address us on the invention of the transistor. Jeff.
Thank you, Alan. So, the 50th anniversary of the invention of the transistor. It was invented at the end of 1947, pretty close to Christmas time, or the very first transistor was, by these gentlemen who were working at AT&T Bell Laboratories in the United States, which is the research arm of the what was AT&T, the telephone company in America. And the inventors were William Shockley, Walter Brattain, and John Bardeen. They were given the Nobel Prize in Physics in 1956 for their work on the transistor, discovery of or the invention of the transistor and the transistor effect. This man, John Bardeen, was given another Nobel Prize with another couple of gentlemen in 1972 for the theory of low temperature superconductivity, and he is one of the only people that I know of who has received 2 Nobel Prizes in the one discipline. So he's a very smart man. So towards these gentlemen were working on properties of semiconductors, and towards the end of 1947 they invented this rather ugly looking device, but they realised that although it was ugly, it was the precursor to modern information technology. And it's called the point contact transistor. By the middle of 1948, Shockley in particular had developed the theory of the junctions inside this device, the internal workings of the device, and had gone on to invent the bipolar transistor, which is the device that I will actually try to explain the inner workings of to you tonight. The precursor to the development of the point contact transistor was the work going on at AT&T Bell Laboratories was basically to find a replacement for all of the switching contact relays that were in the telephone system that switched the calls through the network. And they were looking for a solid state replacement for those devices because mechanical relays wear out, and they didn't want and there is a cost associated with that. they were working in earnest on this problem during the war, just before the war, and then during the war their interest obviously got shifted to wartime projects, and one of those wartime projects was the detection of radar. And they found that the little cat's whisker devices that people had in their crystal sets for detecting radio signals were also very good at detecting radar signals. And so a lot of research during the war went into the properties of these little cat's whisker devices, which consist of silicon or germanium as the main content. And they wanted to know how these little devices worked. So this provided a background, and when Bardeen, Brattain and Shockley started working in earnest on the transistor after the war, they had all of that information about the properties of silicon and germanium that had been built up during the war. So they were looking for a replacement for the mechanical switches and relays in the telephone system, and also for a replacement for the vacuum tube. The vacuum tube was the main component in electronics at that time to provide amplification. Consists of little metal filaments and all sorts of things inside an evacuated glass tube. It's very fragile. If I drop this, it's going to break. It's very time consuming to make, and it's very bulky compared to the transistor. So I've also shown you, for a comparison in size, modern transistors that were developed from the point contract transistor. The diode is one type of semiconductor, and I'll talk about its behaviour. It is also the solid state, or the modern equivalent of the cat's whisker that was used in the radar detectors. The transistor here is what we're going to be talking about, and now the integrated circuit, which is the heart of your computer and a lot of electronic devices. And inside an integrated circuit there are many, many thousands of transistors. Okay? These are all actually to scale on there. Now, paralleling the development of the transistor is the development of the computer. And obviously, the computer has benefited greatly from the invention of the transistor. Early computers were based on these valves and filled rooms. There's one that was constructed in the USA in 1946 called ENIAC, which had more than 17,000 vacuum tubes in it, and it could do 1,000 computations per second compared to the modern PC, which is greater than 100 million computations per second. Australia, in parallel, developed a valve-based computer called CIRAC, and you note that the power consumption was 30,000 watts, and it weighed 7,000 kilograms, which is considerably different to the modern PC. So if the transistor had not been invented, this could be your IBM personal computer, and you would require direct cables from Loyang to actually run it. Or how about your cellular phone? Not very practical if the transistor had not been invented. So what is at the heart of the transistor? And the answer to that is mainly one element in the periodic table, and that element is silicon. The first devices were actually constructed in germanium, but silicon proved to be much more practical material. It's also very abundant. It makes up 26% of the Earth's crust by weight, and it's the second most abundant element after oxygen. So there is plenty of silicon around the world for us to continue making transistors out of for a very, very long time. There's actually another group of semiconductors called the compound semiconductors, which are combinations of elements in this group and an element out of this group. Gallium arsenide is a very common one, and it's used in light emitting diodes, the little red diodes and things that are on the displays on your audio amplifiers and things like that are made out of gallium arsenide. The laser that's in your compact disc player is often made out of a combination of three elements: gallium, aluminium and arsenic. Okay, so various combinations of these two groups can be used to make up these compound semiconductors that have different properties depending on which elements you use. So the behaviour of the semiconductor materials depend on the properties of the atoms that make up the material and how those atoms are joined together in the solid. So we have to look a little bit at how atoms are put together before we can understand the properties of the materials that make up the semiconductors. The simplest element we have is hydrogen, which consists of a single proton which has a positive charge with a single electron orbiting it. The next element in the table is the helium atom, which has two protons, two plus charges in the middle, two neutral charges called the neutrons, and two electrons orbiting it. So you'll note that every time we have two plus charges, we have two minus charges, so that we have a neutral charge balance. So we go on adding protons to the nucleus, protons and neutrons to the nucleus, the core of the atom, and we add electrons to orbit the atom. The electrons, as we add more and more electrons to the atom, they are placed in shells around the atom. And the inner shell electrons are more tightly bound to the nucleus, and the outer shell electrons are comparatively more loosely bound. In the case of silicon, there are 10 what we call inner shell electrons and 4 loosely bound outer shell electrons, and it is those electrons that take part in the bonding of silicon atoms to when it forms a solid. So when we put silicon atoms together to form a solid, what happens is that each silicon atom bonds to 4 of its silicon neighbours. And it does this by sharing an outer shell electron with each of its neighbours to form a neutral network. We can look at this in another way, and that is in terms of the energies associated with the electrons. And quantum mechanics says that when we bind the electrons together in the solid, the bound electrons have energies that fall inside an energy band here, and we call that energy band the valence band. And in the neutral silicon, every atom is quite happy to have these 8 electrons around the outside of it, and it is all the bonds are satisfied. So if we want the silicon to be able to conduct electricity, we have to be able to pull an electron out of one of these bonds, and then it goes off through the solid. And there's a minimum amount of energy required to lift that electron out of the bond and allow it to conduct electricity. So what we talk about is pulling an electron out of this valence band, the energy levels associated with the bound electrons, the minimum energy required to allow it to conduct electricity. And that energy required to rip the electron out is called the band gap energy. So how does a semiconductor like silicon compare to some other solids? So here we have this semiconductor like silicon, and it has the band gap here, and we have to raise electrons from this energy to that energy if we want to conduct electricity. In an insulator, and a good insulator is silicon, combination of silicon and oxygen, called silicon dioxide. These bonds between the silicon and oxygen atoms are very strong, and so a lot of energy is required to rip an electron out and conduct electricity. And so we say that it has a much larger band gap energy. Okay? And the minimum amount of energy required to conduct electricity in an insulator is much greater than it is in the silicon. In metals, when we bond all the atoms together to form a solid, we have quite a few electrons left over. And so these are relatively free to move around and conduct electricity. So in a metal, we say that the conduction band has some electrons in it, which are free to move and conduct electricity. Okay, so the energies associated with the bonds inside the atom define how well it conducts electricity. So and silicon in this state where all the bonds are satisfied is relatively poor conductor of electricity. But it turns out that by adding small amounts of other atoms to the silicon lattice, we can actually change its ability to conduct electricity by an enormous amount. And those atoms that will change the properties of the silicon are the group 3 and group 5 impurities. Boron, aluminium, gallium, and indium, and the group 5 ones, phosphorus, arsenic, and antimony, are the main impurities that are used to change the electrical conductivity of silicon. So let's see how those atoms can change the behaviour of silicon and turn it into a conductor. There we have silicon up the top with its 4 outer shell electrons. When they're all bound together into the solid, there's no free electrons to conduct electricity. Let's add a group 5 impurity. Just change a few of the atoms over to a group 5 impurity. And it has 5 outer shell electrons. So when it bonds to each of its 4 silicon neighbours, like it does up here, it's got 1 electron left over. And this electron is relatively loosely bound in the solid, and therefore it's fairly easy for it to move through the lattice and conduct electricity. By the same token, if we take a group 3 element like boron, it has 3 outer electrons. So I think you can see what's going to happen when we put it into a silicon lattice. Here we have a boron atom down here. It bonds where it can, and this bond is missing 1 electron. And again, it's relatively easy for one of these other electrons to hop over and fill that vacant spot. So again, we've got a mechanism which allows us to move electric charges around inside the solid. These absences of electrons, the missing electrons, are called holes. And it's like they have a positive charge because there's a minus charge missing from the spot, so it's like we have a positive charge there, called a hold. In terms of our ideas of energy, for the n-type group 5 element like phosphorus, we say that this loosely bound electron basically introduces an energy level that's up here close to the conduction band. And it's very easy then, we only need a small amount of energy to move that electron into the conduction band and conduct electricity. By the same token, our p-type dopant, our group 3 dopant, it introduces a energy level down here near the valence band, and it's relatively easy for an electron in the valence band of the silicon to jump up to that energy level, and then we can conduct electricity just by moving adjacent electrons into that hole spot. And as each electron moves, you create another hole as it moves, and therefore you can conduct electricity that way. So we've got these two different types of material. I should mention that you only need to change 1 in a million atoms from silicon to impurity to make a semiconductor that can be useful. So now we've got these what we call p-type material, doped silicon, and n-type doped silicon. N-type has an excess of electrons in it, and the p-type has an excess of these positive charges called holes. So what happens when we take a piece of n-type material and put it next to a piece of p-type material? This is called the semiconductor junction, or PN junction, for obvious reasons. This side has excess electrons, this side has excess positive holes, and so what happens is there's a bit of swapping goes on. The electrons come over here and start filling up holes, and the holes move over there. But this process does not go on forever, because as we move charge from one side to the other, we actually start to build up a voltage. So if we plot the voltage as a function of position, we actually have a voltage difference build up. And in silicon, that voltage difference is about 0.7 volts before it can no longer move more charge across against the voltage gradient that has built up. This separation of charge here is called the depletion region. And you say, okay, we've got a separation of charge, maybe this thing works like a battery. But no, it doesn't, because if we connect a wire around the outside, basically all we do is we create another depletion region. We will move charge from one side to the other until it has built up another voltage difference, and then there will be no more charge transfer. There is an exception to this, which I'll come to shortly, and that is the silicon solar cell. Okay, so the diode is not a battery. So what happens when we do connect a battery to the diode? First diagram there shows you the zero bias, no voltage connected case where we have this separation of charge across the depletion region. If we do what we call reverse biasing the PN junction and connect the battery as shown there, with the plus side going to the N-type material and the minus side going to the P-type material, all we do is end up increasing the size of the depletion region and moving that charge further and further from the interface. So that doesn't conduct electricity when we reverse bias it. If we forward bias it, however, and we put the minus side of the battery terminal to the N-type and the plus side to the P-type, then charge can freely flow across the junction, and we have conduction of electricity. So the PN junction or diode is a one-way device which controls electricity and only allows it to flow in one direction. And if we look at it as a function of applied voltage, in the reverse biased regime we just increase the depletion region and no current flows, except when we apply too much voltage and the device breaks down and conducts and destroys itself. And this is called the breakdown region. So we don't want to run our diode in that regime. In the forward biasing regime, where it's happy to conduct electricity, it's the current that flows through the circuit versus the voltage has a characteristic that looks like that. So it is a steeply rising, the current is a steeply rising function of the voltage applied across the device, which means that if we have a small change in voltage applied, we get a large change in the current through the device, and that's the basis on which your crystal set works to amplify small voltages into large currents and allow you to listen to your crystal set and hear the sound. Now I said there was one exception to the diode not being a battery, and that is the silicon solar cell. The silicon solar cell is basically an unbiased p-n junction, and it's made in such a way that it's a very, very broad junction, so that there is plenty of opportunity for light to interact with the depletion region between the N and P type materials. It turns out that visible light has sufficient energy to be able to kick electrons from the valence band into the conduction band. Okay, so what light is capable of doing is making an electron-hole pair. If an electron-hole pair is made within that depletion region, we have a plus and a minus charge produced, and the minus charge is going to go over here to the plus side hole goes over here to the minus side, and we have a conduction of electricity. And we can actually connect wires to the back and front of this device and use it to as a voltage source. If we actually apply a reverse bias across this junction and make that depletion region larger, we have a device that is very sensitive to light, and it is called a photodetector, and it is the basis on which your video camera works to change the light that comes in into electrical pulses which are digitally stored. Okay, so that's the PN junction. William Shockley realized that you could do something if you made up a device that looks something like this. And what we have here is a slab of N-type or N-type material sandwiched between two slabs of P-type material. By the same token, we could take a slab of P-type material and sandwich it between two N-type materials, and we have the basis for the bipolar transistor. At each of these interfaces between the P and N type materials, we have a depletion region. We'll have the separation of charge across that interface. The negative charge will move across there, and the holes will move across there. And the same token, the same thing happens at that interface, so we have these two depletion regions. A properly biased transistor is formed when we apply a large reverse bias across this interface here, and we call that the base collector interface, or junction there. So what we do is we apply our battery the right way so that we form a large depletion region. And then over here, we actually forward bias the other junction. So what happens is, you remember that with forward biasing, charge is free to flow across the junction into this material. If we make that slab narrow enough, what happens is that this charge makes it across into this other depletion zone, and it then is accelerated by the large potential difference across there, and most of the charge actually ends up going right through the second junction, and we get a large flow of current. We get, in the forward biased section, there's actually a very small current that flows out through the base, and we say that this is the emitter region, so it emits the charge or injects the charge from this side into the reverse biased other side of the thing, of the transistor, and we get a large current flowing through this way. But that current, you'll note that that current cannot flow until we forward bias this section of the transistor. By changing small changes in the voltage applied, the forward bias voltage applied here, will create large changes in the current that flows because of the characteristics of the diode structure. So that's the basis of the transistor acting as an amplifier. Small currents in the small changes in the forward bias section create large changes in the base collector region of the transistor. Now the transistor also acts as a switch, and I've got this fairly simple circuit set up here. And what we have is a properly reverse biased base collector region of a transistor. We have a light emitting diode which will light up when current flows through this section of the circuit. We have a switch down here in this section, and we have two current meters, one A1 and one A2 there, so that we can register the currents that are flowing in those two regions of our circuit. So when we close, you'll note that this section of the circuit is complete, but this section of the transistor is reverse biased, so no current flows until we complete the forward biasing in this section of the circuit. So when we close the switch, we see that we have two currents registered in our current meters, A1 and A2, that you can see up there. The current through A1 is very small compared to the current through A2, through that part of the circuit. So a small forward bias and a small forward current creates a large large current through the other part of the transistor. This is the basis of the transistor as a switch, and is the basis on which your computer stores the ones and zeros that are the binary coding that your computer uses for information storage. So each memory element in your computer essentially has a single transistor which switches on or off, and we get a 1 or a 0 depending on whether that transistor is switched on or off. That's how the information is encoded in the memory of your computer, ones and zeros corresponding to the code of your computer program. And and the central processor unit of your computer is the thing that juggles those ones and zeros depending on the computer what they are represented of in your computer program. So that's a simple transistor as a switch. Now I'm going to jump ahead to modern integrated circuit technology and say a few things about how these transistors are actually formed in silicon. And silicon is actually grown as a crystal, and in modern growth of silicon, they actually create crystals that are about 25 centimetres in diameter, so that's about 8 inches in old terms. And the devices are actually formed on the surfaces of wafers, which are cut out of these crystals. Very thin wafers are cut out of these crystals, and the devices are actually formed in one side. Here we have, this is not an 8-inch crystal, but a much smaller crystal of silicon, and it's highly polished on one side, and in your integrated circuit, the devices are actually all formed just on one side of the silicon wafer. And in fact, they sit within about 1/1000th of an inch of the top surface of the wafer. I'll say a little bit more about how this is achieved. Early devices were actually formed by just changing the impurities that were being added to the crystal as it grew, so that this crystal would have an N region, a P region, an N region, and then they would just cut the crystal up and form the transistors. Then they realised that it was going to be far more practical if they used what is called planar technology. And this was invented in about 1959. And the various regions that are required to make the transistor were just formed in one side of the crystal. It's obvious why it's called the planar device technology. So the N and P and N type regions are defined by bringing appropriate atoms into close proximity with the circuit, the surface of the material, heating it in a furnace, and they then diffuse into this region. So we would bring it in contact with, say, N-type material, that would move into there. Then we'd put some P-type material in contact, move that through to make the base region, and then put some more N-type material in to form the collector region. Then we would add metal contacts to the outside. So that's the first bipolar transistor, formed by planar technology, and as it says here, that was about 1.5 millimetres wide. The modern integrated circuit or computer memory circuit uses a variation on the bipolar transistor, or on the transistor, called a field effect transistor. And it controls or switches on the flow of current through the device with a thing that is called a gate region. And essentially this can be done by having, let's say, this region as N-type material and putting two P-type materials here, and then the depletion regions between here can be changed by changing the voltage, and that can act as a gate to squeeze off the flow of current through the device from the source to the drain. So this is the field effect transistor. Oddly enough, a man called Julius Lilienfeld was granted a patent for a device that looked quite like this in 1930, which is 17 years before the point contact transistor was invented. It wasn't based on silicon or germanium, it was based on copper mixed with some other elements. And no one has been able to make this device work, even though this guy was granted a patent for it. And it took until 1952 for Shockley to actually invent the field effect transistor and demonstrate it in 1953. So this device, which is the basis of modern computers, was given a patent in 1930, but it was sort of lost until 1953. So in 1959, we had transistors that were about 1.5 millimeters wide. In 1981, this is a computer memory element, a random access memory element with about 300,000 transistors in it, and each transistor is 0.009 millimeters wide in that case. Just going back to the planar technology for a moment, how are these regions defined so that we can add the atoms in, to add the impurities into those regions? They're actually defined by a process which is called photolithography, where you define the regions on the silicon sample wafer where you want your device to go by using a mask, a photographic mask on a glass plate. You put a photosensitive chemical, smear it across the surface of your sample, expose the photosensitive material through this mask so that you can see the shadow of the region that you want to define on your material formed onto the photoresist. And the chemistry of the photoresist changes to make it either easier to remove or harder to remove, and so you can then etch away or remove the material that has been changed by the exposure of light, and then you have a gateway in which you can introduce the atoms, the impurities that you want to change the local regions to form the collector, the base and the emitter. And obviously if you've got 300,000 transistors, you can't just define all of those with one mask, and each device that you produce will require many masks to be used in sequence to define all of the regions on the device. But it's extraordinarily successful technology. This is actually not done as a one-to-one process. The mask that is used is actually something like 10 times or so larger than the regions, and a demagnified image is formed onto the material through a lens. And the modern circuits, the lenses that are required to form the demagnified image onto the material cost $1 million a piece, because they have to be so carefully produced. So let's have a look at the number of transistors per chip as a function of time. One of the co-founders of Intel, Gordon Moore, in 1965 predicted that the number of transistors per chip would roughly double every 18 months. And if we look at memory elements in your computer, we can see that he's been pretty close to right so far. The central processor units, the things that do all the mathematical crunching inside the computer, have fallen a little bit behind, but they're not doing too badly. The computer memory is certainly keeping up with Moore's law. So what are the sizes of current elements inside your Pentium processor? Current technology has device sizes within the computer that are about 0.4 of a million a thousandth of a thousandth of a millimetre, so it's 0.4 microns. Compared to some of the things that we are accustomed to, the human hair is about 100 microns. Here's our 1 micron line width in our computer, and we're now at about half that. Red blood cell is about 7 microns. Bacteria. So you can see that if you are defining modern transistors in a fabrication plant, you have to get rid of all human hairs and all dust particles, because the devices you're forming are smaller than the dust particles, and so the fabrication plants have to be extremely clean. A modern fabrication plant for microcircuit costs about $2 billion to construct. I just wanted to show you, this is the table which shows the projected requirements for devices up to the year 2010. And there's one pretty amazing thing, well, there's quite a few amazing things. This is the projected device size as a function of year. And there is a requirement, iron, the presence of iron is an impurity in these devices, it's deadly, and it will just shut down a circuit. And so the requirement is that the impurity levels of iron in a circuit, in a wafer, can only be 5 times 10 to the 10 atoms per centimetre cubed. And silicon is 5 times 20 times 10 to the 22 atoms per centimetre cubed. So that means that 1 atom in 10 to the 12 can be an iron atom. The silicon that is used in modern integrated circuits is the cleanest or the most pure material that man has produced. This information comes from a consortium of companies in America. Things like Intel, AT&T, Bell Labs, IBM have all banded together to form this consortium called Sematech, which received government funding from about 1985 or so to win back America's predominance in the semiconductor field. And they have basically been able to achieve that through all working together. Okay, what of the future? As I said, the costs are going up and up as the device sizes go down. Several $1 billion per new fabrication plant. Photolithography has basically about to reach a dead end, because the device sizes are now close to the wavelength of the light that is used to expose the used with the photolithographic masks to expose the photoresist. And the scientists are now madly looking for the next way of illuminating the masks, and it may be X-rays, but each different technology that may be used costs a lot of money to research, and so places like Intel and IBM are all banding together to work out where they go for the next reduction in device size. So it's quite clear that to date the development of the transistor has been a phenomenal one, and it has allowed great things to be done, but it also, because of the low cost of individual transistors, it can also do very cheap party tricks. And so here we have the transistor can actually play its own birthday tune. This actually has a light pipe that runs through it, And when we light the candle, the light is fed down into the base. And now we've got two transistors doing this. And there's a little microcircuit that actually plays Happy Birthday, and it's based on a transistor. Okay, thank you for your time. It won't stop for a little while.
Very good, Jeff. Yes. Take some questions.
Yes.
Jeff has agreed to take some questions, so following this wonderful lecture, I ask you now to address your awful questions. You always want to ask about
Shut up.
including the birthday.
I went to a lecture here a few months ago. We had a scientist from Israel who was talking about diamonds. Are they in the step with transistors as well?
Diamond, yes, people have spent a lot of work trying to dope diamond. And I forget which type, one of the doping types has been achieved in diamond, but the other one has not been achieved. So you can't do both of the doping that's required to make something like a transistor. And now people have actually, there's more hope in materials like gallium nitride, which is one of these 3-5 semiconductors, but it has a very wide band gap like diamond, and so it will have similar properties to diamond and similar uses. It's not going to stop. I've created a monster.
As I understand the limitation of the size of the transistor is manufacturing limitation.
At present, yes.
So what is the limitation based on atomic?
On physics, yes, that will occur when the gate regions in the field effect transistors are of the order of 0.005 microns, and then quantum mechanics takes over, and it's not going to be clear whether the device is switched on or off. It becomes a probabilistic problem, and let's put it in a bucket of water. Here. Yeah. So quantum mechanics takes over. Probability becomes important, and you will not be able to tell whether the device is actually switched on or off, on or not.
So if you follow the trend line,
Yes.
what year?
They've only gone through to the year 2010, and that's 0.07 microns, so there's an order of magnitude to go beyond that. Okay? But the photolithography is a really big problem that's coming up. I like that. Right. Well, funnily enough, you can actually use silicon to dope gallium arsenide, and it behaves differently depending on whether it sits on an arsenic site or a gallium site. Okay, you can understand how it would behave differently depending on which of those two sites you put it on, because the bonding would be different. Okay, so that's one of the things that's used. So you use these group 4 guys.
Demonstrated the transistor on or off by using a mechanical switch.
Yes.
So there aren't mechanical switches.
No, but you can essentially cascade things. You can use other transistors to feed other transistors. So it's a multi-transistor. Each transistor switches the next one along. there's been lots of work on, which I'm not, widely familiar with, on organic computers, using single atoms as elements in computers. But these things are a long, long way from realisation as a technology. And people are still learning how to deal with the materials and what are the most appropriate materials to use. So it's a long way before it'll turn into a device.
Yes. You described earlier in the lecture that when you apply a strong voltage across the PN junction in such a way in the reverse direction so there's no current.
Yes.
Is it the voltage is high enough?
You actually.
There's a breakdown, there's a large current. Can you describe the process?
Well, essentially what you're doing is you're ripping the electrons out of those bonds. You are actually providing enough energy through the voltage of the battery to rip electrons straight out of it, and you're breaking bonds inside the material, and that's why it destroys itself. Well, yes, they do break down and conduct electricity. I don't. Sorry? I don't have one of the Zener diodes.
Characteristic.
Oh, the characteristics.
Yes.
Oh, essentially, yes. All right. This one. So yes. Why do Zener diodes not destroy themselves when they? I'm not quite sure why that is. I'd have to look it up. Look at it again. Sorry. Well, there is the whole visible spectrum is capable the photons have sufficient energy to do that. You have to move into the red region and the infrared before you don't have sufficient energy to excite them. But yes, there is an efficiency associated with different wavelengths of light. Oh, in the transistor. Yes. Well, I mean, holes are just electrons going in the opposite direction, essentially, because hole conduction occurs because we've got electrons hopping to fill the vacancy, and so electrons are going in the opposite direction. So there's no real problem with the movement of these holes. Holes are electrons going the other way. So they should be out. They're free to move as the electrons are. It's just the way you think about it, and that it's useful to think of these holes as being a positive charge moving.
Yeah, not only that, but there's actually a very close correspondence between what's happening to the electrons in these old vacuum tubes, in the sense that electrons are flowing from metal surface to metal surface through a vacuum where there's nothing. The electrons and the holes, indeed, inside the bulk silicon crystal, actually are travelling through almost like free space. They go through that silicon crystal with virtually no impedance whatsoever.
That's right.
So it's quite a deal of correspondence. Anyway, we've hit our limit of 9 o'clock. So I think we'll thank Jeff, and just remains for me to remind you all that if you can come out again next week on what's bound to be another cold night here in Melbourne, then there will be a further edition of the July lectures on August the 8th at 8 o'clock, once again here. On that occasion, the lecture will be given by John Ellis, who is visiting the School of Physics at the moment, and it'll be on the subject of particles and the cosmos. So we welcome you here back next week into the same place at the same time. It remains for me to ask you to join with me to thank Jeff. There's wonderful lecture.
Sorry about that.
Let it do.